Alright, so you're going to have to get good at doing calculations that involve equilibrium, especially with acids and bases. So there are a couple of things that we have to know before we try and solve a problem like this. It says the pH of a 0.1 molar solution of formic acid, HCOOH, at 25 degrees Celsius is 2.38. Calculate Ka for formic acid at this temperature. So more than likely, we probably don't know exactly how to solve this problem. So let's address a couple of things that we should at least know. So here it says the pH. Well, you know that pH is equal to negative log of the hydrogen concentration or hydronium concentration. Either one is fine. For now, I'll just go ahead and keep that hydronium representation, but it literally could have just been H plus as well. So we know that that's what pH is. And it tells us that for this case, the pH is equal to 2.38. It also tells us that the concentration of the solution is 0.1 molar. And what we're trying to find is Ka. Now, some of us, I know it's been a long time, probably don't know or might ask, what is Ka? Now, remember, when we talk about equilibrium, K anything is always talking about your equilibrium constant. So Ka just means your acid dissociation constant, which sounds scary for maybe some of us who pay a lot less attention in class, but it just refers to your reaction of an acid dissolving in water. So you should always know what the products of that is. You're just stripping off a hydrogen from that acid, and that goes to the water, which is going to form your hydronium, and then your conjugate base is left over. So let me go ahead and write out the reaction for the acid dissociation of formic acid. Alright, so I wrote the reactants, but before I tell you what the products are, let's just see if you can figure it out. Formic acid is a monoprotic acid. What that means is it only gives up one hydrogen. If you look at the formula for formic acid, you have two hydrogens. Can you figure out which is going to be the hydrogen that is going to be given away? I'll give you half a second, and then I'll give you a couple more seconds. Alright, hopefully you pick this one. Why? Because this is the hydrogen that is bonded to an electronegative oxygen. This one will not be donated. So your products are going to be, well, if this hydrogen is going to be picked up by the oxygen on the water, then the bond, and I'll rewrite this, it's HCOO, and then it's bonded. This bond right here is going to turn into a pair of electrons onto what's going to become formate. So our products are going to be H3O plus HCOO, and because it has that extra pair of electrons now, it's going to end up getting a negative charge. So if we wanted to write the Ka for this, remember, Ka is just products over reactants. Now, since we do have an acid dissociating in water, your products are going to be aqueous. So aqueous hydronium and aqueous formate ions floating around in water. Ka is just products over reactants. So of these substances, not all of them are going to come out in your equilibrium expression. The only ones that are going to come out are the ones that are gas or aqueous state, right? Solids and liquids do not come out. So the only one's going to come out is formic acid, hydronium, and formate. So our expression for Ka is going to be products over reactants. So the concentration of the hydrogen ion or hydronium times the concentration of the formate ion divided by the concentration of formic acid. So since we're being asked to find Ka, in order to do that, we have to know what H3O plus is, we have to know what the concentration of formate is, and we have to know what the concentration of formic acid is when this is at equilibrium. Now, some of us might be thinking this. We might be thinking, oh, I already know the concentration of formic acid because I was given the concentration of the solution here. And you might be thinking, oh, I can find the concentration of hydronium because I know the pH. So if the pH is 2.38, then I can work backwards to find the concentration of hydronium. And for the most part, you're half right. The true statement is yes, if you know the pH, then you'll be able to find the concentration of hydronium. That's perfect. But that 0.1 molar concentration of the solution is not going to be the concentration at equilibrium, because when formic acid is placed in water, some of its concentration is going to go down to form hydrogen ions and formate ions. So let's get one thing out of the way first. Let's go ahead and calculate the concentration of hydronium. So hopefully you remember that from this equation here, you can rewrite it. The concentration of hydronium in any situation, this equation will always be true, is equal to 10 to the negative pH. So we want to find the concentration of hydronium. That's going to be 10 to the negative 2.38, which comes out to 4.2 times 10 to the negative 3. And so of the three, we just found one of them. And one of the very, very nice things about the dissociation of monoprotic acids is that when it breaks up into the two ions that make it up, if you know the concentration of one of the ions, you know the concentration of the other ions. So not only did we find the concentration of hydronium, the concentration of hydronium is also equal to the concentration of formate. So the concentration of formate is also 4.2 times 10 to the negative 3. We're just following simple stoichiometry. Now we just have to figure this out. Enter the Rice table. So R stands for reaction. So I went ahead and wrote the reaction. I did not put water as a reactant because it doesn't come out in the equilibrium expression anyway. So I stands for initial. So when we talk about initial, we're talking about the initial concentration. So what is the initial concentration of formic acid? Well, here you got it from the prompt. The initial concentration of formic acid is 0.10 molar. So we know that. And the initial concentration of hydronium and formate are going to be 0, because we don't have any hydronium or formate ions until formic acid starts dissociating. So initially we just have 0.10 molar formic acid. And now we have to figure out the change. Now we know that the change, this concentration is going to go down, and this concentration is going to go up. And because we're respecting the stoichiometry, since the coefficients are 1 in all the cases, it's minus 1x plus 1x plus 1x. If this was a 2, then it would have been plus 2x. But that's not the case. All right, and well, what's nice is that we solved for x. We know what x is. X is 4.2 times 10 to the negative 3. So in each of these cases, it's plus 4.2 times 10 to the negative 3, plus 4.2 times 10 to the negative 3, and this one is minus 4.2 times 10 to the negative 3. So at equilibrium, the concentration is 0.10 minus 4.2 times 10 to the negative 3. At equilibrium, our hydronium concentration is 0 plus 4.2 times 10 to the negative 3. And same thing for formate, 4.2 times 10 to the negative 3. Well, now we can calculate this, and that's going to give us 0.0958, which, if we were to round to two significant figures, gives us 0.10. So I know earlier you might have thought, oh, well, that was the concentration that was given to us in the prompt. That's not always the case. Depending on what the pH is, depending on what the concentration is of the hydronium ion, the concentration of the solution is not necessarily always going to be very, very close to your equilibrium concentration. But for this case here, that happens to be the situation. So now we know the concentrations of the three substances that come out in the Ka equation. So we can solve for Ka now. For Ka, it's always going to be the product of the concentration of your products, which are the ions that make up the acid. So in this case, so any anion would be represented here. Of course, in this case, it's formate, so HCOO minus over, and then the concentration of your acid, formic acid. So now that we know the values, we can plug them in. So it's going to be equal to 4.2 times 10 to the negative 3, and we can actually square that since both of these values are the same, they're equal to each other, divided by 0.10. And this is actually going to come out to 1.8 times 10 to the negative 4. And so this is how you find the Ka of a solution given the pH. And usually you're doing this for the dissolution of weak acids. The next slide in your PowerPoint is talking about percent ionization. And percent ionization for acids literally just means what percent of your acid dissociated. So percent ionization is equal to the concentration of your hydronium ion at equilibrium divided by whatever the initial concentration of your acid is. And so here, notice that I put HA. Well, remember, acids are represented by H something, where that something is your anion. In the previous example, our anion was formate. But it could literally be anything. It could have been HCl, HF, H2SO4, H3PO4, HCOOH, right? So the equation is your equilibrium concentration of hydronium divided by your initial concentration of your acid times 100%. So if we wanted to find the percent ionization of our previous example, we know that the concentration of hydronium was 4.2 times 10 to the negative 3. We would have divided that by the initial concentration, which was 0.10 times 100%, and that would have come out to 4.2%. Okay, so that was actually considered an easy equilibrium problem. It gets a little bit tougher. Here we have a scenario where instead of calculating the Ka from the pH, you have to find the pH given the Ka. So they didn't give it to us here, but I'm going to go ahead and provide it for you. The Ka for acetic acid, the dissociation constant of acetic acid, is 1.8 times 10 to the negative 5. Again, since this is Ka 1.8 times 10 to the negative 5 is equal to the ratio of your ions that make up your acid divided by the concentration of your acid. So we're talking about acetic acid. The equation for the dissociation of acetic acid in water is right here. So you have your acid. This acid is going to give up a hydrogen. The water is going to pick it up. You're going to form hydronium and acetate. And I removed water from the equation because it's not going to come out in our Ka expression. Our Ka expression is going to be equal to the concentration of hydronium times the concentration of acetate over the concentration of acetic acid, HC2H3O2. So right now, all that we have to work with is the Ka of the solution. We have the Ka of acetic acid, and we know that the initial concentration of the acetic acid is 0.3 molar, and we have to find pH. So hopefully you're thinking of rice. All right, so let's write down what we know. We have acetic acid, which is HC2H3O2, and this is going to dissociate or break up into hydronium and acetate, C2H3O2 minus. Okay, so here's our little grid here. So I stands for initial. What are our initial concentrations? What do we know? Well, we know that the initial concentration of acetic acid is 0.30 molar, and because we're looking at acid dissociation, before it actually dissociates, we have no hydronium, we have no acetate coming from the acid. And now the question is, well, what's the change? Well, for all acid dissociation processes, the concentration of your acid is going to go down, and the concentration of your hydronium and anion is going to go up. And because this is a monoprotic acid, right, we're going to form the same amounts of ions. So it's going to be plus X and plus X. And that means that at equilibrium, our concentrations are 0.30 minus X, 0 plus X, 0 plus X. All right, so you have to remember the end game here. At the very end, we want to find pH. Well, in order to find pH, we want to take the negative log of our hydrogen concentration. Well, we know that our hydrogen concentration is X. So how are we going to solve it? Well, if we know what the concentrations are, even if we're using variables to represent them, at equilibrium, and we know the Ka, we can solve for X. And once we solve for X, we can calculate the pH. So we know that Ka, which is 1.8 times 10 to the negative 5, we know that that is equal to the concentration of H3O plus, which is X, times the concentration of acetate, which is X, divided by the concentration of 0.30 minus X. So we have one equation and one unknown. So algebra says that we can solve for it. What is X going to be equal to? So if you haven't figured it out already, this is going to be equal to X squared over 0.30 minus X. That's going to be equal to the 1.8 times 10 to the negative 5. If you start rearranging things, the quadratic formula is going to come to mind. Now, I know you might cringe at the thought of the quadratic formula, so I'm going to tell you something that's going to make this very, very nice. Anytime your Ka is very, very small, we're talking 10 to the negative 4, negative 5, and smaller, you can make this very interesting assumption. That means that your X, your amount of hydronium that is existing, is going to be extremely small. So just let's think about it. Ka is the ratio of products over reactants. If Ka is very, very small, that means you have a very, very small concentration of your products. So 0.3 minus an extremely small number is still going to be 0.3. So we can actually make an assumption. We can say that this x value is so small that 0.30 minus x is going to be 0.30. So we can kind of remove that and make this problem a lot easier to solve. So if we rewrite it, it'll look like this. We'll get the 1.8 times 10 to the negative 5 is equal to x squared over 0.30. And then we can just move that over to the other side, and we'll get 5.4 times 10 to the negative 6. That is equal to x squared. So rearrange, solve for x, and x will come out to 2.3 times 10 to the negative 3. And this is nice. We just found x. And if we go back to our rice table, we know that x is the concentration of this of hydronium, your H+. So if x is 2.3 times 10 to the negative 3, now we can take this number and plug it into our equation to solve for pH. So we just have to do the negative log of this. And when we do that, we get 2.64. And that is our answer. All right, so that's my little explanation. That's from your PowerPoint, but I think hearing it from me and kind of seeing me draw it out, work it out might be better. I'm going to go ahead and email you guys out. Hopefully you watch this video before the lecture, because I'm going to give you some practice problems to work on tomorrow, or today. It's today, so all right. It's 2:30 in the morning. Okay, so yeah. All right. I'll send this out in a moment. I'll see you in class. I'll continue to awkwardly end this video. All right. I paused the video and then I push record again. It's not over yet. You shouldn't even be listening to any more of this video. The lecture's over.